Let's consider one of the most important concepts in all of finance, the time value of money. The value of a pile of money will change over time. The nominal value of that pile of money will grow over time because it can earn interest. And the real value will shrink over time because of inflation. The nominal value, recall, is the actual number of dollars in that pile. And the real value is the purchasing power of those dollars. Now, whether you get richer or poorer in real terms depends upon the relative rates of these two forces. Inflation, a rising general level of prices, reduces the real value because the dollars in that pile can now buy less. The interest earned by the dollars in that pile will add to its height, but its height has the potential to grow exponentially if interest is compounded from period to period. Einstein called exponential growth the most powerful force in the universe. Exponential growth is the force that created the ability of the height of a sheet of paper, when folded over 50 times, to be tall enough to reach the sun. Let's consider the financial application to this concept of exponential growth, often referred to as the miracle of compounding. Suppose you deposited $100 into a bank account that earned 10% interest per year. From period to period, the growth rate is a constant 10%, as you can see by those little blue arrows down at the bottom of the chart. If the periodic interest was computed strictly off the original principal of $100, the average annual growth rate would be 10%. This is how the concept of simple interest is computed. Simple interest is continually computed based upon the amount of the original deposit. Compound interest, on the other hand, computes interest based upon the continually updated principal. From compounding period to compounding period, the principal will grow by the amount of interest accrued in the previous period, and thus the compound interest earned in every period after period 1 will be greater than that which was computed by simple interest. Look, for example, at the interest earned in period 2. It's $11. If interest was computed by the simple interest method, that amount would have been $10, 10% of the original deposit of $100. However, because compound interest is based upon the cumulative amount of principal in the account, and because the $10 interest earned in period 1 was added to the original principal, the interest earned in period 2 is $11, 10% of $110. And this process continues like a snowball rolling downhill. It keeps getting larger and larger. In period 10, the interest earned was $23.58 using compound interest. If the simple interest method were used, it would have still been $10. Look at that red arrow. It won't be long until that thing becomes almost vertical. The blue arrow, on the other hand, represents the growth of the account had the simple interest method been used to compute interest earned from period to period. As you can see, as time goes on, the difference between the two becomes greater and greater. Now, we'd like to know how much money would be in that account after some period of time, say 20 or 30 years, without having to draw all these blocks. If the simple interest method were used, it wouldn't be a problem at all. We'd simply use the formula for computing interest earned, which is I is equal to P times R times T, where I represents interest earned, P represents the original principal, R represents the interest rate, and T represents the number of time periods, that is, the number of years. Then we'd simply add that amount of interest earned to the original principal to find out how much was in the account. In this case, the total interest earned would be 100, which is the principal, times 0.1, which is the interest rate, 10%, expressed as a decimal, times 10, the number of years in which the account earned interest. You multiply all that together, you get 100. So that is the amount of interest earned, and when we add that to the original amount, 100 plus 100 is equal to $200 will be in that account at the end of 10 years. But look at the amount of money in the account that we have after 10 years when we use compound interest. Instead of $200, we have $259.39. Computing the amount of money that would be in the account in some future period is a little more involved when the base principal adjusts from period to period. When we consider the previous interest earned in the computation of the interest that could be earned in any given period, we must use our time value of money calculations. The time value of money calculations will come in 4 different varieties, as we will see. The future value of an amount, the present value of an amount, the future value of an annuity, and the present value of an annuity. In this particular case, we'd want to use the formula for calculating the future value of an amount. Here's the formula for computing the amount that will be in an account after accruing interest for one period. FV stands for future value. That's the amount that will be in the account at some point in the future. PV stands for present value. That's the amount of the original deposit. That's how much you deposited today. The expression 1 plus R represents the rate of return, expressed as a decimal. For example, a 7% rate of return would be expressed as 0.07. Therefore, we must add 1 to the rate of return, otherwise PV times R would be less than the original present value. That would indicate that the amount in the account actually went down. If you deposited $100 into an account that would pay an annual interest rate of 7%, how much would be in that account at the end of 1 year? Let's plug these values into our formula for computing the future value of an amount. And what we see here is that FV, future value, is equal to $100 times 1.0.07. Not surprisingly, we see the future value of that account at the end of period 1 is $107. Okay, so now let's look at another example. How much would be in that account at the end of 2 years? So notice that the subscript 2 has been inserted to indicate that we are now computing how much will be in the account at the end of year 2. Notice that the expression in that blue box represents the future value of the account after 1 year. This represents the adjusted principal. The original principal was $100, but the principal for year 2, upon which the computation of interest for that period will be based, is $107. In order to see how much will be in the account at the end of period 2, we simply multiply that adjusted principal at the end of period 1 by the growth rate in order to let it grow for another year. This entire expression will then give us the future value of the deposit after 2 periods. Let's simplify the expression by removing the brackets. The expression 1 plus R times 1 plus R can be expressed as 1 plus R quantity squared. Note the relationship between the subscript on the left-hand side of the equation and the exponent on the right-hand side of the equation. These will always be equal. In English, This equation says that the amount of money in the account at the end of period 2 is equal to the original deposit, the present value, multiplied by 1 plus r squared. As you might guess, the amount of money in the account at the end of period 3 is equal to the original deposit multiplied by 1 plus r cubed, and so on. Let's generalize the above expression so that it applies to every case. Note that the 2's have been replaced with n's, where n represents some number. So the period for which we want to compute the future value is the same as the exponent to which we raise the growth rate. N would represent the number of compounding periods, the number of times the principal upon which the interest is computed is updated. For our examples for now, interest will be compounded, that is, added to the principal, only once per year. Let's now answer the question in example 2 above. If you deposited $100 into an account that would pay an annual interest rate of 7%, how much would be in the account at the end of 2 years? Check out the steps of the computation, and you'll see that the total value of the account will be $114.49 at the end of the 2 periods. Take a few moments to answer this question. How much would be in the account at the end of 2 periods if we used the simple interest method of computing interest? Pause the video if you have to, because I'm going to give you the answer in 5, 4, 3, 2, 1. Using the simple interest formula, I equals P times R times T, where T is the number of compounding periods, in this case years, only $14 would have been added to the account by the end of year 2, whereas using the compound interest method, $14.49 would have been added to the account. The account doesn't grow as fast using the simple interest formula because interest is always based upon the original value of the deposit. Using compound interest, the principal upon which the next period's interest is based is always updated from period to period by the total amount of interest that was previously earned. So now check out the problem in example 3 above. How much would be in the account at the end of 10 years? The total amount, $196.72, is verified by my having worked this out on an Excel spreadsheet. Rather than multiplying the original deposit of 100 by the 7% growth rate to compute the value of the account in each period, as would have been the case had we used the simple interest method, I multiplied the previous period's amount, which was updated by the amount of interest earned to date, by the growth rate. As you can see, the result from the spreadsheet verifies the result of the formula for computing future value. Using the simple interest formula, we can see that only $70 would have been added to the account, making the total value of the account $170. So everything is probably seeming pretty straightforward to you at this point, and it will become more and more intuitive as you get some practice doing the time value of money exercises that you'll find in Module 2. But there's one little issue that I'd like to deal with before we move on. There may be a potential problem in using this formula. Suppose you're trying to solve this problem using a calculator that doesn't have an exponent function. You'd have to multiply 1.07 times 1.07 10 times. This could be a real pain, especially if you're computing future value over the next 30 or 50 years. Turns out, this value has already been computed for you. It's called the Future Value Interest Factor, or FVIF. In fact, this and virtually all other future value interest factor coefficients can be found in one of the time value of money tables in Module 2. In Module 2, you will find a set of tables that you can download and print out for the time value of money problems that you'll need to compute not only for the first test, but for every test thereafter. So I'd advise that you practice up and get good at it. Click on the Time Value of Money Tables link to download the tables. When you click on the link and start printing them out, you will find that there are 4 sets of tables: the future value of an amount, the present value of an amount, the future value of an annuity, and the present value of an annuity. We'll deal with annuities a little later. But for right now, let's use the tables to solve an earlier future value problem that we had solved with a formula. Here's our good friend example 3. If you deposited $100 into an account that would pay an annual interest rate of 7%, and you let that 7% compound period after period, how much would be in the account at the end of 10 years? This is clearly a future value problem, so we'd want to use the table for the future value of an amount. In the tables that you download, this table is entitled Future Value Interest Factor for $1. Here's how we'd set up the problem in its general form. The future value is equal to the present value times the future value interest factor given a certain rate and a certain number of time periods. This is the basic template we will use for solving time value of money problems. For this particular problem, the template looks like this. The future value is equal to the present value times the future value interest factor at 7% for 10 years. So the first thing we need to do is to find this future value interest factor on the future value of an amount table. You can find the relevant future value interest factor on this table. Just look across the row of rates along the top of the table and the number of periods listed on the left side of the table and find where they intersect. Let's see if we get the same answer using the tables as we did with the formula. So in the above problem, R, the rate of growth, or the interest rate in this case, is 7%, and the number of compounding periods, in this case years, is 10. There's our 7% growth rate and our 10 years of growth, and here's where they intersect. The future value interest factor, when the growth rate is 7% and the number of periods over which it is compounded is 10, is 1.9672. Plugging that value into our formula, we get $196.72, which was the same answer we got using the formula. Now, there are some cases where, rather than starting with the present value and computing the future value, we'd start with the future value and work back to the present value. For example, suppose that for some reason you were to receive $1,000 in 8 years, but between now and then there was a 6% average annual rate of inflation. That inflation is going to eat away at the real or purchasing power value of those dollars. You would want to know what would be the purchasing power value of that $1,000 received in 8 years relative to what a dollar would buy today. In other words, what is the present value of that $1,000 to be received 8 years from now? To compute the present value, we just use the same formula we use for computing the future value. We'll just use some 8th grade algebra to transpose the growth rate to the other side of the equation. Let's just do a little more manipulation, all strictly within the rules of algebra, to make this thing easier to look at. Okay, so now let's do the problem. We'll start by plugging in the values that we know into our present value template, and then solve for the unknown. Take a moment to make sure you understand where these numbers come from. Pause the video if you need to. The 1,000 is the amount that you will receive in the future. The 6 represents the rate of inflation, and the 8 is the number of discounting periods. 1.06 to the 8th power is 1.5938. 1 divided by 1.5938 is equal to 0.6274. So that $1,000 that you'll receive 8 years in the future, given the 6% average annual rate of inflation during that time, will buy the equivalent of what $627.40 will buy today. As you may have already guessed, the value in the red circles, same value just in 3 different forms, has already been computed for you. It is called the present value interest factor, the PVIF, and can be found in the present value of an amount table. Here is the present value of an amount table. And here is our present value interest factor given a 6% rate of inflation for 8 years. So you really didn't have to make all of those calculations. You just use the table. Take a moment and challenge yourself to compute the following present value problem that's very similar to, but not exactly like the present value problem we just solved. Suppose the government informed you that you had overpaid your dog license bill by $500 last year. Now, they will gladly refund your money, but it will take them 6 years for it to clear all the red tape. How much will that $500 buy you in terms of today's dollars if the average annual rate of inflation over that period of time will be 9%? Use this table, the present value interest factor of an amount, to solve that problem. Pause the video and come back when you've got it solved. If you had trouble, when you come back, I will explain exactly how it's done. So how'd you do? Hopefully you got it right. But if not, that's okay. Don't get discouraged. It takes some practice to get good at it. So here's the first thing that you have to do in solving these present value or future value or any time value of money problems. First, identify the variables. Here's the future value, the amount you're going to receive in the future. Here is the number of years. And here is the discount rate. Of course, we're using the rate of inflation as the discount rate. There are other present value problems in which we will use some other rate, but we'll get to that later. Second, make sure you're using the present value of an amount table. It's easy to get careless and accidentally use the future value table, but you'll notice that all of the coefficients in this table are fractions, that is, they are less than 1. All of the coefficients in the future value tables will be greater than 1. So it appears here that we're using the correct table. Thirdly, locate the intersection of the coordinates. Remember, the rates are along the rows, the number of years down the column. We have a 9% inflation rate for 6 years. The intersection of those two coordinates is at 0.5963. That's our present value interest factor. So now that we know the PVIF, we can set up the problem as a formula. Here we see our present value problem in both the general form and in a form that's more specific to our current problem. I like to call them templates rather than formulas because they're pretty much the same for all time value of money problems. Just a little tweak here or there, depending upon whether you're solving a present value problem, as we're doing here, a future value problem, as we did earlier, or a present or future value of an annuity problem, which we will consider in another video. In each case, the process is the same. So the major issue in doing time value of money problems for a test is to identify the correct template to use. Once you do that, you're 95% of the way home. Just plug in the values of the variables that you know and solve for the unknown. All we need to do now is plug in the future value and the present value interest factor from the present value table. And there they are. So you see, your $500 that the government is holding will only be worth $298.15 in real terms by the time you get it back. In our previous present value problem, we wanted to compute the real value of some amount that would be received in the future, discounted by the rate of inflation. But there's another reason why we would want to discount, that is, compute the present value of some future amount. And for this reason, we'd use a different discount rate. There will be frequent occasions in your life where you'd have to choose between two alternative investment opportunities. One that will pay you a certain amount after a given period of time, and one that will pay you even more, but only after a longer period of time. Your task would be to determine which of the two investment opportunities is the better deal. The solution would be to compute the present value of the two future amounts, and the alternative with the greater present value would be the better deal. Suppose that option A would pay you $1,000 in 5 years, or option B would pay you $1,200 in 8 years. To see which of the two is the better deal, simply compute the present value of each of the two amounts, and the opportunity with the highest present value would be the better deal. In this case, opportunity B would be the better deal. In this case, opportunity A would be the better deal. Because we are already experts in computing present value, the decision as to whether option A or option B is the better of the two is not going to present much of a problem. However, there is one issue that we have to consider before we move on. The question is, what should we use as the discount rate? It would seem intuitively obvious that just as in the previous present value problems, we'd use the rate of inflation as the discount rate, just as we did in this illustration. After all, we're trying to maximize the real or purchasing power value of our income. However, by using the rate of inflation as the discount rate, we are ignoring the fact that we could reinvest the returns we received early, in this case from investment A, and by the time we were to receive the returns from investment B, the cumulative returns from investment A would be greater, as illustrated in the graph below. Using the rate of inflation as the discount rate would indicate that investment opportunity B was the better investment. However, actually, investment opportunity A is the better investment. What do we do to deal with this issue? Rather than use the rate of inflation as the discount rate in this case, we use something called the required rate of return. A set of lecture notes on the required rate of return, what it is and why we use it, is in the lecture notes section of Module 2. Make sure you read and understand that brief essay. Post questions and comments to the discussions board. Your goal, for test purposes, is to distinguish when you should use the rate of inflation as the discount rate and when you should use the required rate of return. Generally, you'd use the rate of inflation when you want to know the real or present value of some future amount. You'd use the required rate of return when you are comparing two different amounts that will be received at two different points in the future. Now we only have one more issue to deal with, and then you will be a total expert on the present and future value of an amount. And this issue arises when you know both the present and future values, but you're solving for either the rate of return or the time period. Consider the following example. What annual rate of return on investment, or interest rate, would you need in order to convert $2,000 into $4,000 in 10 years? Since you know both the present and future values, you can use either the present value template or the future value template to solve this problem. Let's use the future value template in this case. Here's the future value template in its general form, and here it is after having filled in the values that we know. The future value is $4,000, the present value is $2,000, the number of years, the exponent, is 10. What we're solving for is R, rate. So let's just use a little more 8th grade algebra to move that 2,000 over to the left-hand side of the equation and divide it into 4,000. Now we have 1 plus R to the 10th equals 2. Solving for R is easy by use of the time value of money tables. Since we set this up as a future value problem, we'll need to use the future value table. We know that the number of compounding periods is 10, so we'd find the 10 along the N column. Let's go ahead and highlight that row so we won't lose our place. Now, along this row, we need to find a 2. That's not exactly 2, but it's as close as we're going to get using the tables. You could get exact results down to the last decimal point with the use of a financial calculator. There's a link to a video about using financial calculators in Module 2. Now that we've located the future value interest factor that is close as possible to 2 on this future value of an amount table, we can just look up to the top row and see what the necessary growth rate would be. As you can see there, a growth rate of about 7% will get us to our desired goal of turning $2,000 into $4,000 in 10 years. Once again, if we used a financial calculator, we could see exactly, down to the last decimal point, what the necessary growth rate would be. So there's one last variation on this theme. This time, let's use the present value template to solve for the number of time periods, although we could have just as easily used the future value template. If I could get a 5% rate of return on some investment or interest rate on a savings account, how long would it take for $10,000 to grow to $15,000? Here's our present value template in its general form. And here it is with the values filled in. Let's use a little more 8th grade algebra to move that 15,000 over to the other side of the equation. Pause the video if you need to see what I did there. Because we set this problem up as a present value problem, we need to use the present value of an amount table. Now, locate the 5% growth rate column. Look down that 5% column until you find something reasonably close to 0.6667. Although not exact, it's close enough for our purposes. So as you can see, it takes about 8 years to turn $10,000 into $15,000 at a 5% compounded growth rate. You are now an expert on solving present and future value of an amount problems. We still have a little ways to go now because now we have to deal with annuities. But don't let that term annuities frighten you. It'll be very easy and go real fast because now you know the basics of time value of money math. Don't forget to check out the practice problems in Module 2.